All right, folks, here's the test review um, video for Chapter 7. Here we go. Um, Number one, according to DuPont 2007 Global Automotive Color Popularity Report, 19% of all cars, so right there's a nice hint. That's talking about the population, so this is going to be a parameter. Um, all of the 19% of them were white. In a random sample, samples create statistics. Um, Sample of 100 cars parked in the long-term parking, 22% of those cars were white. Okay. All right. So it's essentially asking you guys if you know which one is a parameter, which one is a statistic. So which one is it that lines up? I think it is B. That matches up with what I was just getting at. Yep, 19% came from the population, so it's a parameter. 22% came from a sample, so it's a statistic. Bam. Number two, the best statistic for estimating a parameter has which of the following characteristics? I've already copied and pasted an explanation of the answer here. Um, you want low bias. I think that kind of goes without saying. High bias is meaning that the sampling distribution, the mean of the sampling distribution is not accurate. Low bias is what you're looking for, so it's A, C, D, or E. And high variability means a high standard deviation. You don't want that. You want low variability. You want your graph to be centered around mu, and you want it to be tighter. If you have high variability, it would be more spread out like this. So the purple one there is low variability. Okay. And this explains it in a booky type of way. Low bias means the statistics sampling distribution is centered around the parameter. Low variability means the typical value of the statistic is close to the parameter. In other words, they're not too spread out. Um, all right. And it kind of comments on why C is wrong. Um, since a statistic should always equal the parameter it's estimating, there should be no variability. That would mean like you've got the standard deviation down to like nothing, which is not possible. Unless, well, you'd have to have a massive sample size. Number three, which best describes a sampling distribution? And I've again kind of copied the answer down here. Whoop. The answer is E. Let's go through it though. Um, the distribution, a sampling distribution, the distribution of all the values of a statistic found in a large number of simulated samples. So that's the problem with this one. It's not a large one. In favor of looking at part E, it's all possible. Okay, there's the difference there. That's why I like E better than A. Letter B, sometimes it's helpful to look at the other ones that are wrong and talk about why. A sampling distribution is it the set of all values of a variable in a sample? Um, no, that would be essentially describing the population itself, and that's not what we're doing. C, the set of all values of a variable in a large number of samples. There's that large number again. Okay. No. Um, the distribution, sorry, of parameter values in all possible samples. No. So, why is that one wrong? The distribution of parameter values in all possible samples of size n. I need to think about this one. Oh, duh. It's not a distribution of parameter values. It's a distribution of statistics. So it's not parameter values. Like, um, where every sample you get creates a statistic, not a parameter. That's why. I knew it would come to me if I thought long enough. Number four, In a large population, the mean IQ is 112, standard deviation is 20. Suppose 200 adults are sampled, there's n. The sampling distribution of the sample mean IQ is, so we're taking a whole bunch of samples of 200, finding the mean. Which one is it? So the first thing it's getting at is, should the distribution be normal or approximately normal? Exactly normal or approximately? We never, ever, ever say exactly. So just, okay. We always say, well, it's approximately normal. Probably not perfectly normal, but approximately normal. So it's B, C, or D. Notice the means are all 112. That's good. So then essentially, which one has the correct standard deviation? The standard deviation of x bar is sigma divided by the square root of n. Sigma was given to us as 20 divided by the square root of 200, and that will be 1.414. So it's C for number 4. 5. In a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of these trees show signs of damage. Which of the following statements is correct? The sampling distribution, part A. The sampling distribution of the sample proportion of damaged trees is approximately normal. I think that might be it right there. We might have gotten it on the first try. And why is this? Because how large was the sample? It was 100, and 100 is greater than or equal to 30. So this is the central limit theorem. Well, let's read the others real quick to see why they're wrong. If we took another random sample of trees, we would find that 40% would show some signs of damage. This kind of freaks me out. It's worded too strong. Not all the samples are going to be exactly 40%, you guys. That's not right. They're going to have some variability. C, if a sample of 1,000 trees was examined, the variability of the sampling distribution of the sample proportion would be larger than the sample of 100 trees. It's the exact opposite. You had 100 and you increased it to 1,000. Increasing sample size will always reduce. So if this said smaller, it would have been okay, but it didn't, so it's not C. D, the standard deviation of the sampling distribution of damaged trees is this formula. This is actually the standard deviation formula of a binomial. So it's the wrong formula. Okay. Boop, boop. And so it's not E. 6. Which of the following statements is true when taking a simple random sample from a large population? All right. Oh, it looks like I've already circled the answer. The answer is going to be all 3 of these. Let's talk about why. The sampling distribution of x bar has a standard deviation of sigma divided by root n, even if the population is not normally distributed, and that is true. All distributions, you can find the standard deviation no matter what the shape of the population is. What you actually need to know to find standard deviation is you have to know that each trial is independent, but it's not really getting at that. So this is indeed true. Check. 2, the sampling distribution of x bar is normal if the population was normal. That is true. So if your population is a nice normal curve, and then you take a sampling distribution of x bar, it will also be normal, okay? Check. Number 3, when n is large, the sampling distribution of x bar is approximately normal, even if the population was not normally distributed. That is true. This last one is getting at the central limit theorem. This is a little vague. It says when n is large, it has to be greater than or equal to 30. So maybe you're thinking to yourself, well, I'm not so sure about this one. So I could understand an argument why you would choose A, but I think it's leading you to think, well, it's large. they want you to say that is true. Okay, so I could see a lot of kids picking A on this one, but it's all three. 7, suppose you're sampling from a distribution that is strongly skewed left. Which of the following statements about the sampling distribution of the sample means true? Um, so I drew it down here. Here's the population. It's strongly skewed left. Um, and it will, the sampling distribution of X bar, that's a lousy, sloppy X bar, but so it will be normal. It will be approximately normal if n is greater than or equal to 30. So that's what this is, part A is saying. A is the answer. As your sample size increases, the shape of the sampling distribution gets closer and closer to a normal distribution. And that is correct. It was the population's distribution is this, but it will become more and more normal the larger your sample gets. And we have made that cutoff at 30 to where we are like, fine with approximating it as normal. Let's read the others to see why they're wrong. As the sample size increases, the shape of the sampling distribution gets closer and closer to the population. No, that would be saying as n gets really big, it goes back to this shape. It stays with the population shape, and that's not true. Because again, we're sampling the average. So this population over here, let's see, the mean would be a little bit left of center. Okay, we're essentially taking samples to find the green line. We're not taking samples that will model the entire shape. We might have one sample here, and then here, and then here, and one might be right on the green line, another one on the green line. And all your samples are going to be bunched in around here like this. So you take enough samples to look like this. You might have one a little further left because it is skewed, but those ones that are fewer left are going to be few and far between the more samples you take. So it will eventually look normal. C, as the sample size increases, the mean or the center of the sampling distribution gets closer to the population mean. That's not true. Remember this formula that the average of the X bar is mu regardless of sample size. In other words, this center is always mu. Taking a larger sample size doesn't move this green line either way. Okay, it is what it is. D, regardless of the sample size, the shape of the sampling distribution is similar to the shape of the population distribution. Well, that's clearly wrong based on everything we've been talking about. E, regardless of the sample size, the standard deviation of the sampling distribution is approximately equal to the standard deviation of the population. It's saying it doesn't matter how big your sample is, the spread over here will equal the spread over here. That's not true. The larger your sample gets, this one will get tighter and tighter and tighter. So sample size directly affects standard deviation. All right, 8. Suppose we wish to estimate the percentage of students who smoke cigarettes at each of several colleges and universities. Who smokes anymore? 2 of the colleges are Wabash, and Wabash is small. There's only 900 kids there. And Purdue is big, 36,000 kids. What should the relative size be of the samples from each school if we want the 2 sample distributions to have the same standard deviation? Okay, um, and there's the answer. It's D. Standard deviation of a sampling distribution depends on sample size. Okay, it does not matter. The population size does not matter. Okay, as long as you meet the 10% rule. The 10% rule shows that each student being selected is independent of the one in front of it, or the student before or after them. Um, that's important, but the population size doesn't matter. So the sample sizes should be the same. They're trying to kind of trick you to be like, oh, look, one school is bigger than the other school. So Purdue's bigger, so we should take more kids from Purdue? No. Um, or maybe the opposite of that. They're trying to get at that with you. Um, so, the formula for both of them would be this. this was how you would find the standard deviation for both schools. So you would just want n to be the same. And this is this is more about independence. You can't take more than 10% of each school's enrollment, otherwise they won't be independent, but that's not what it's asking. 9. In order to use this formula, this is the formula that gives you the standard deviation for a sample proportion. To calculate the standard deviation of the sampling distribution of the sample proportion, which of the following conditions must be met? So I wrote down what they are. This first one, you're like, I've seen that before. What's it for, though? This is the large counts. The purpose of it is to know if the sampling distribution is approximately normal. Okay? That has nothing to do with using this formula for standard deviation. So it is not number 1. So you can get rid of A and D. 2, the population's distribution has to be approximately normal. That is also not true because even non-normal distributions have a standard deviation. Okay, so it's not that one. So it's not B. So yeah, it's not E. So we know it's going to be C. Winner, but why? The sample size is less than 10% of the population size. Again, to calculate standard deviation, we want to know that trials are independent. It is the only requirement to use those formulas. Last multiple choice question. Labor force had a census in a large metropolitan area. For the time it takes for people to commute to work has an average of 20.5 and a standard deviation of 15.4. So right here, this is my mu, and this is my sigma. What's the probability that a random sample of 40 people, that's my n, have a mean commute time that is greater than 25 minutes? So it's a mean, so this is x bar. Okay, and which one would it be? Well, first of all, this stands out to me right away. Greater than 25 minutes. Well, I'm going to cross off. Oh, they're all greater than. Never mind. I thought I was being sneaky. They're all greater than. So we're good there. We want to do x bar minus mu over standard deviation divided by root n. So which one does that? X bar is 25, so it could be this one, or this one. Okay, so I can cross off A and E. Bam, bam. Next, we're subtracting mu. There's minus 20.5, minus 20.5. They're all doing that. Okay, so which one has the correct standard deviation? This one just takes just sigma, so it's not doing any dividing. We need to divide by root n, and the only one that does that is that one. This one did 40 minus 1, so no, not that. So the answer is B. All right, on to the FRQs. A certain beverage company is suspected of underfilling its cans of soft drink. Oh, no way. The company advertises that the cans contain, on average, 12 ounces. So there's my mu with a standard deviation of 0.4. There's my sigma. For the questions that follow, let's assume the company is telling the truth. In other words, these are the parameters, okay, of the population. Can we calculate the probability of a single randomly selected can that it has 11.9 ounces? If so, do it. If not, explain why not. But we cannot do this, okay? It's a no-no. We don't know the shape of we'll say of the population. It never says it. It doesn't say it's approximately normal. And if our sample size is a single can, n equals 1. So that n1 is not greater than 30. So we cannot model with approximately normal. We can't do that. So we should not go ahead and find a z-score, so we stop. B, a quality control inspector measures the contents of a simple random sample of 50 cans. Okay, now we're good to go because 50 cans is good and 50 is greater than or equal to 30. So boop, we can say it's approximately normal and we're off to the races. We can do this one. Okay, they calculated the X bar of all the samples of all 50 cans. Okay, what are the mean and standard deviation of the sampling distribution of X bar for samples that have 50 cans? Okay, well, the average sample will equal the average of the population, which we wrote down up here. So on average, each sample will hover right around 12. I should get better at using my units. This would be 12 ounces of liquid. Okay. The standard deviation of X bar equals sigma over root n, and sigma up on the top was 0.4, and we're divided by the square root of 50. That is 0.0, I should do squiggles, 0.0566. Okay. All right. So the inspector in part B so the inspector that was taking 50 cans at a time obtained a sample mean of 11.9 ounces. Of X bar was 11.9 ounces. Calculate the probability that a random sample of 50 cans like this produces a sample mean amount of 11.9 ounces or less. So there's my less than sign. Be sure to explain why I can use a normal calculation. Because 50 is greater than 30, the central limit theorem applies. The central limit theorem tells us the sampling distribution is approximately normal. Okay, so now that I've explained why, let me do the work. The probability of X bar being less than 11.9, that's what we're asking. We need to find well, what's the z-score for this? Oh, I'm going to draw a curve. Okay. I know that 12 is the average in the middle. I know the standard deviation is 0.0566. I'm going to take a little more time on this one, okay? So if I take and I move down one standard deviation, and I try to fill this curve out with a little bit more detail. One standard deviation down is 11.94. I'll stop there. I won't put the 3, 4. If I subtract another 0.0566, now I'm at 11.89, we'll say. Okay. Let's go up a standard deviation or two. This would be 12.0566. Oh, I can't believe I used the calculator for that. Oh well. And then plus 0.0566 again. So this line would be 12.1132. Okay. So I like doing that, guys, because now I can see the curve, I know what I'm dealing with, and I'm trying to do the probability that you get a sample less than 11.9. And actually, 11.9 is like almost right on this line. It's just a smidge above, right? And less than. So I can already tell it's going to be a small probability. If you remember the empirical rule, 68% in there, 95% is within here to here. That's 95% in here. So I can already get a pretty good estimate. This sliver and this sliver are each each 2.5%. So I'm guessing my answer is going to be 2.5%. So let's find a z-score. So my z is 11.9 minus 12 divided by 0.0566. Whoops, 11.9, whoop, divided by 0.0566. Oh, it's not as close to -2 as I thought. Maybe I have some faulty thinking somewhere along the line. They're at 1.77, we'll say. So this would be the probability of a z-score being less than -1.77. And I can do a normal CDF with that. So in terms of z-scores, I'll change my color up. I have -1.77 and way over here would be -99, like way down here. So when I do my normal CDF button, it's -99, comma, -1.77. So that's my answer. You could also look this z-score up in your green packets. It's 0.038. I wasn't too far off when I was kind of trying to eyeball it. I said it's going to be about 2.5%. It's about 3.8%. D, what would you conclude about whether the company is underfilling its cans of soda? So, do we have sufficient evidence of we did uh, we did all these samples. We got an average of 11.9 when we had 50 cans, okay? And that was all based on the assumption that 12 is the average. So since a sample like this will only occur by chance 3.8% of the time, we have convincing evidence that they are underfilling their cans. And take time on these guys. Don't sell this short. All right. The cutoff, remember, for like what's significant is a 5% mark. Okay, and we are underneath that with 3.8%. Okay, if indeed 12 is the true average of their cans, then getting a random sample to be down here is really unlikely. It only happens 3.8% of the time. So when a sample is collected like that, it makes us seriously doubt the initial claim. Last one, number 12. An opinion poll asks a sample of 500 adults whether they favor giving parents of school-age kids vouchers that can be expressed for education. Oh, this isn't the last one. There's a 13. Sorry. That can be exchanged for any private or public school of their choice. Each school would be paid by the government on the basis of how many vouchers it collects. Suppose that in fact, what is it? What do they mean by in fact? 45%. They're telling you folks, this is the population parameter. Okay. In other words, it is P. Okay. 45% of people favor this idea. What is the mean of the sampling distribution of P hat? Remember that the mean of P hat equals P, which is 0.45. In samples, yeah, sorry, in the proportion of adults in samples of 500 who favor blah, 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 blah. That is how you do the first one. Part B, what is the standard deviation? The standard deviation formula is the standard deviation of p hat equals the square root of, it's, no, I'll write it both. It's p and 1 minus p. Remember, I do not use p hat for this. I use the parameter. So it would be the square root of 0.45 times 1 minus 0.45 divided by 500. Be very careful on your calculator. The whole entire shebang is under the square root, and you should get 0.0222. Okay, they're building for us, you guys. We are finding the average, the standard deviation. Is it normal? We're building. Can we use the normal approximation? Okay, so this is large counts. Do it with a sample of 500, is NP and N1 minus P, are they greater than 10? So N is 500 times 0.45. That's going to be way more than 10. 500 times 0.45. So in other words, we call those successes, I guess. We would expect 225 people to be in favor of this voucher system. And then 500 times 0.55, well, that would be everybody else. That would be 275. Remember, successes and failures always add up to the total sample. That's how I did that without touching my calculator. So, yes, the distribution of p hat is approximately normal. All right, then we finally take a final analysis using pretty much all this, knowing that it's normal. What's the probability that more than half the sample are in favor of this voucher system? The probability that p hat is greater than 0.5, right? Half is 50%, okay? So what is the z-score for 0.50? It would be 0.50 minus 0.45 divided by the standard deviation. If you forgot this, let me slow it down. This is p hat minus p divided by p1 minus p over n. Okay, but we already had all that, right? P hat is the 50%. P is the population parameter they asked you in part A, and this is the standard deviation, which you found right there. When you do that, you get a z-score of 2.25. So it's a pretty large z-score. So this would be the probability of a z-score larger than 2.25. If you wanted to sketch the curve, you could. 0 is on your z, well, let's say both ways. 45 is the middle, and we're over here at 0.50 for more than half. So we're doing this. As a z-score, 0 is the middle, and we got a z-score of 2.25. And way down here would be 99. So we can do normal CDF, 2.25, comma, 99. Oh, this is not likely. Not likely at all. Squiggle, squiggle. About 1.2% of the time. Okay? So more than half the people would be in favor. The probability that more than half the people would be in favor of this in a sample, how big was our sample? A sample of 500 people, that would only happen 1.2% of the time. Last one. This one's really the last one. All right. A small internet mail order company keeps track of the number of orders it fills every day for many, many years. It's saying, like, hint, hint, folks, this is a parameter incoming here. Okay. Um, it's the whole population, is what that means. It determines the distribution of the variable orders filled that day is roughly symmetric. Okay. And it has the following 5-number summary: minimum, Q1, Q2, Q3, and the max. Suppose we take a random sample of size 40 from the distribution and calculate the range for each of the samples. Okay. Below is the dot plot of the ranges of the 50 samples. So they would, I don't know how many data points are in here, but it's many, many, many years. So it's a lot of data points. Okay. Um, so the question is the sample range an unbiased estimator of the population range? Use the dot plot above to justify your answer. So this is the result of a sample, 50 samples, so there's 50 dots here. Um, is it unbiased? Remember, biased means it under or over estimates the population, the parameter. So let's look at this. We know the parameter because we're talking about range. What is range? Range is max minus min. Okay. So what is that? We have max of 80 and a min of 20. So we know the parameter is 80 minus 20. We know it is 60. Okay. So looking at this, do you think, well, where do you think the middle is? We could count 25 dots in and find the median. 25 plus 25 is 50, right? Let's try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Well, that's a little, I don't know if I have that perfectly, but let's just say it's right there. So there's our median, 57. So you might be looking at that going, look at that. It should be 60, right? Sorry, it should be 60. And they only had 4 samples that were 60. It's underestimating it all the time. And this one's a sneaky one, you guys. It is actually not biased. Um, because samples of 50 will only be, they're only going to be 60. Think about this. The only samples that will be 60 are what kind? The only samples that are 60 will be samples that had they had the max and they had the min in the sample. So it's very understandable that every single estimation of the range is going to be smaller. And the fact that it's only like a median of 57 is actually pretty darn close. Um, so it is not a biased estimator. Um, okay. Yeah, and that's a tricky one. Okie dokie, and also it looks, it looks fairly symmetric too, which is a good sign that it's not biased. So let me say it one more time. Um, or you could pause and back up. The the sample would only obtain a range of 60 if 80 and 20 were both in the sample of 50. If it had the max and the min. So just by the way this is set up, a sampling distribution is always going to be a little bit lower than 60. So it it's very sneaky. So you might think, well, look, it's 57, so it's constantly underestimating. Um, but in this case, this is actually pretty darn close, and given the fact that we're doing range, we kind of give it a little bit of leeway. Now, if we were sampling X bars should be spot on. Okay, but we're not doing that. We were doing a range. You know, all these dots represented a range. All right, that's that, folks. Have a great day.